Hello, hello. Here we are, retro Diels-Alder reaction. Okay, so as the name implies, and as you can see from the reaction schematic, this is basically the opposite of what we talked about in the previous video. Namely, we take a cyclic product and we end up breaking it back into the individual diene and the individual dienophile that comprise that ring system. Now, the way that this works out is that you gotta do this at really high temperatures, and I'm not talking, like 50 degrees Celsius, 70 degrees Celsius. Now, I'm talking like some serious heating, like easily 150 to 250 degrees Celsius, like that high, for this to work out. If you look at the energy values for the bonds, these are the bond dissociation enthalpy values specifically. The carbon-carbon single bond is worth 347 kilojoules per mole. The double bond is roughly, worth 614 kilojoules per mole. If you look at the cyclic molecule, technically speaking, in that cyclohexene structure, we have 5 single carbon-carbon bonds, and we also have 1 carbon-carbon double bond, which we have to break to consider the outcome right here. If you look at the diene, within the fragment of what's the cyclic portion, right, we have 2 double bonds and we have 1 single bond right here, which is where the conjugation is present, right? The dienophile will only have the carbon-carbon double bond to consider as far as the geometry of the cyclic structure. So if you just kind of look at the bonds, right, what this will tell you is that, okay, multiply the value of the single bonds by 5 because of the 5 single bonds in the cyclic structure, multiply the value of the double bond by 1 because you only have 1 double bond in the cyclic structure. And that's everything that you have to break in the reactants to lead to the products. Now, speaking of the products, we have 2 carbon-carbon double bonds from the diene, but we have 1 more from the dienophile. So basically, just go ahead and multiply the carbon-carbon double bond value by 3. And then we also take into account that there is the 1 carbon-carbon single bond. So when you do the analysis right here and carry the math, you find out that this equates to about 2300 for the reactants, about 2200 for the products. So in essence, to undergo a retro Diels-Alder reaction, to break the ring, you do have to put in energy. This is an endothermic reaction. And this is one of the reasons why you have to heat the reaction considerably, right? The formation of the ring, in essence, is the favorable stuff. That's what the molecules will want to do. However, comparing the reactant to the products, you should realize that you only have 1 reactant, whereas at the end of this retro Diels-Alder reaction, you have 2 products. So the entropy of the products is actually positive compared to the reactants. And if you recall from your good old days of Gen Chem, the spontaneity of a reaction is given by the master equation, the Gibbs free energy equation here, which shows that the entropy will make the Gibbs free energy be negative, which is good for spontaneity, as you do increase the temperature, right? The higher the temperature becomes, the greater this T delta S term is going to become. And if the entropy is positive, then this negative T delta S will make delta G more negative. So having really high temperatures for these reactions will ensure that you actually undergo the retro Diels-Alder reaction, right? So this is totally an entropy-driven event. It's not thermodynamically the preferred route, but entropy is making it happen so long as the temperature is high enough for that. All right, now, so that's one aspect that you'll have to keep in mind, specifically because you'll be doing something like this in one of your labs, most likely. You'll have to break up a cycloaddition product into the diene and the dienophile, and then you can do some further chemistry with them. So this is actually something that we tend to do in chemical labs relatively often. Okay, but there's another thing that you could also do. You could play not just by, with changing temperature, but you could also play with the idea of changing the chemistry of a molecule via photo-induced events. So in order to understand this, we have to go back to the orbital picture and remember that the HOMO orbital of the diene is the one right here where you have the last 2 electrons present. whereas the LUMO orbital of the dienophile is the one here that doesn't have electrons, right? All right. Now, if you're only heating up the reaction, these are the orbitals you're dealing with. You're dealing with um, the most stable electron configuration in relation to the molecular orbitals, the ground state, right? So that HOMO has to interact with this LUMO, and that will give you the reaction that leads to the cycloaddition product. Now, on the other hand, if you actually expose chemicals to specifically UV light, that's high enough energy that what you can do is promote electrons from a lower level, the HOMO specifically, up to the next level. You don't bring all of them, of course, but you can bring one of the electrons from the HOMO, the previous highest occupied molecular orbital, to what used to be the LUMO. And by doing that, the orbital that used to be the LUMO is now the, well, technically speaking, the SOMO, the singly occupied molecular orbital, but it's no longer a LUMO. So then this becomes the orbital that you have to account for when doing an addition reaction. But if you kind of look at it, one thing that you might realize is that, okay, it doesn't work out exactly the same way as before, because the orbital here that used to be a HOMO had shading on the top on the left, shading on the bottom on the right. Over here, we have shading on top on both sides, the left and the right side. So this is going to change the rotation of how the reaction, basically carries itself forward, and ultimately it will change the regiochemistry of the molecules, right? So this photoinduced type of reactions can be very useful if you know what you're doing with them. Okay, so let me show you exactly what's going on with this photoinduced reaction, right? So here you have your UV lamp that I forgot to highlight in the previous slide. Okay, so you basically expose the molecules to UV light, and just so that we're on the same page, this is not something that you do, just like a second or 2 seconds. Like, you literally have to have this in either a sealed compartment, or just a fume hood where you have blocked all the actual windows, because you have to have UV lights, shining on this thing, and you have to have the UV light shining on it the whole time. So it's basically a lamp that has to be turned on the entire time and in front of the reaction vessel for this to work out. All right, so we said in the previous video, right, that if we do photoinduced, this is going to be the orbital of the diene that we're going to now be using, because now we promoted one electron to the next available orbital, making this the, quote unquote, HOMO orbital of the diene. And once again, to remind you, we have the left side and right side of the diene have the same type of shading as you look at them. So when you draw the diene right here, notice you have shading on the top portion on the left and shading on the top portion on the right. Okay, so we've selected the proper one. And then this is just the LUMO of the dienophile. So what you should realize is that now the orbital on the left for the dienophile is unshaded on the top. So that means that we need to rotate this left side of the molecule on the diene to the left, because that will bring the unshaded portion closer to the dienophile. On the other hand, the orbital on top on the dienophile is shaded, so we do not want to rotate this clockwise. Instead, we want to rotate this counterclockwise, just like the left side, so that we bring the shaded orbital closer together to the dienophile. So what this is going to do ultimately is move the hydrogen on top, as you see right here. Methyl will now lie below the hydrogen as this moves counterclockwise. And similarly here, if we do counterclockwise rotation, the ethyl will end up position above the methyl, right? So that's what you're seeing right here once that happens. And once again, right, the cyanos were trans to each other, so they still remain trans to each other. So the ultimate outcome is that we basically have changed how the ethyl and methyl groups are positioned in respect to each other. So this is technically a distereomer of the Diels-Alder product that we would get if we only did this under thermal conditions and no UV light exposure whatsoever. So you can literally change the stereochemistry and the regiochemistry of these things just by doing that. And it's a really nifty nifty approach. And I mentioned to you this in the earlier video that, it wasn't exactly known what the heck was going on with the Diels-Alder reactions, when they first were being investigated, because this is what people were saying. You could do the reactions, by heating them up, and you were getting one kind of regiochemistry. You did them by exposing them to UV light, you were getting a different distereomer. And then if you change the number of pi electrons that you were dealing with, that would also change the outcome. So it was a big nightmare until Diels and Alder started looking at this thing from the point of view of orbitals, and then everything became clear. So this is pretty powerful. This is pretty awesome, actually. Okay, so in the next video, we're going to talk about the rest of these reactions where we do actually change the type of pi systems that we're dealing with, in terms of the pi electrons, and we'll see how doing the reaction under thermal conditions differs from doing the reaction under photoinduced conditions. So see you in the next video.